In this section, we're going to talk about different types of sounds and signals, and attributes of sound such as pitch, which is our perception of the height or lowness of sounds. Pitch is closely related to frequency, which is given in cycles per second, or hertz, as we talked about before. We'll also be talking about noise, which is a way to characterize sounds that don't have a clear pitch. To do this, we're going to record something into a sound editor, Audacity in this case, which is available free. Synthesize. All right, I will trim that. We can zoom in and see the entire waveform. First, we notice a couple of things. This period looks very different from this section through here. Let's zoom in on this part, which happens to correspond with the I sound in synthesize. First thing we notice is that there's a smooth, repeated period, which corresponds to any pitchy sound. Any sound that we perceive as pitchy is going to exhibit this kind of behavior. And so this is the pitch period, and we'll notice that it repeats over and over again. If we actually zoom out a little bit and just play this section, synthesize is what I said. If we scroll down a little further to the synthesize, so the sound, we'll notice it has a slightly different wave shape, but we notice it still exhibits that periodic repetition. If we were careful and went back and looked at the I, we would notice that the periods are actually shorter than they are in the and even shorter than in the part, where I'm saying synthesize. The section, these are the periods. There's 1, 2, 3, 4, 5, 6 of them. Where I'm coming out of the synthesize. And that longer period corresponds to a lower pitch. So basically the pitch period and the frequency that corresponds to the repetition rate in cycles per second are inverses of each other. And that's a characteristic of pitchy sounds. Continuing our inspection of this waveform, let's look at the consonants. So here's the S part of synthesize. So when we say synthesize, we start it with a long S. And if we zoom in on this closely, we'll notice that there's no repeated period. There's no pitch in there whatsoever. We don't perceive it as a pitch. We perceive it as a high sound, but it doesn't have a pitch that we would correspond to a note on the piano or something that we would sing. And if we keep zooming into this, we'll notice that it just looks like random variations in the signal, which is characteristic of noise. Let's zoom back out, and actually if we look at synthesize, there's some more S sound, and if we zoom in, still sounds like the S. We'll notice that it still is random in its appearance. And then finally, the Z sound at the end, which is also an S. And so those are the consonants as opposed to the vowels, the noisy parts as opposed to the pitchy parts. So we've looked at that recording of me saying the word synthesize in the time domain, which is the waveform that represents the variations in voltage or quantized and sampled words inside the computer as a function of time, going from left to right. Let's look at it in a different way by calculating what's called a spectrogram, which is a plot of the energy at each frequency going up and down, with low frequencies at the low part and high frequencies at the high part, as a function of time, still going from left to right. So now, instead of looking at the shape of the waveform, we're actually looking at something about the high or low qualities of all of the sound at each point in time. I'm going to zoom in a little bit more, and one thing we'll notice is we can see some interesting structure. Synthesize. So there's synthesize. We're still saying the same thing, but the consonant part now looks like this. The vowel part, sin, synthesis. So there's the sin. These stripes correspond essentially to the pitchy part of the sound. And so this lowest stripe is a frequency, which says it's about 300 hertz, which corresponds to the pitch of my voice. These other stripes correspond to harmonics of that, which we're going to be talking about quite a bit more in the future. Note that the noisy parts look like just fuzz in between the pitchy parts, and we can see the actual pitch change in the size when I say synthesize, and my voice pitch goes down. We can see it goes from higher pitch to lower pitch. So the spectrogram is giving us a clue as to the pitchiness, the noisiness, and all of the mix of things that go together to make the sounds that we're hearing. It also gives us a little clue into the difference between the I and the sound, and yet another. But we'll have to look at spectra in a different way in order to really get to the nature of what's different about those three pitchy sounds. So we already know quite a bit about sound just from looking at the waveforms and spectra of different parts of sounds as they evolve in time. We've seen some differences between pitch and noise, and there is one other important attribute of sound, which is loudness. Loudness is our perception of the power or intensity of sound and is closely related to the amplitude of the waveform, but most closely related to the power in the sound. In digital signals, power is computed by adding up the squares of the individual samples. This means that if we want to know the power of a segment of audio, we can just square each sample in that segment, add all those up, and divide by the total number of samples in that segment. Let's look at a demo in Chuck that calculates power in real time and displays something useful based on that. Here I'm calculating power by connecting the analog to digital converter to a gain unit called a squarer, but I connect it twice and set that gain unit to multiply those two inputs together. Therefore, it squares the input signal. All of that's piped into the black hole, which is basically like a speaker that doesn't make any sound. It's there so it can draw samples through this network in Chuck. I drop into an infinite loop, and every millisecond I check the output of that squarer. If it's louder than some level, I print out a special message that says it's loud enough. Otherwise, I just print out the power. Let's run that and see what happens. Loud, loud, soft, not loud enough. Shh. So it doesn't care what kind of sound I'm making as long as it's over a particular threshold. Wow, we're already using DSP to categorize the nature of sounds. So let's go a bit further by figuring out how to use DSP algorithms to determine if a signal is pitched or noisy. When we looked at pitchy signals, we noted the periodic oscillations. I'm going to run a program now that will help us look at that in real time. When we looked at pitchy signals, we noted the periodic oscillations. As we notice in this waveform, ooh, if there was just a way to determine regular epochs in this waveform, like the peaks, time the difference between the peaks, or count the number of peaks per second or per period, we could determine the pitch period and therefore the pitch. Comparing this to noise, shh, we see again that there's lots and lots of wiggles and no regular repetition. One way to determine pitch in a waveform like this is to time the space between regularly occurring epochs epochs, like peaks in the periodic waveform. This is great to do by eye, but it's hard to do by computer algorithm. We also noted that noise is characterized by lots of rapid, random fluctuations in the waveform. So there aren't any regular peaks with regular spacings. There's just lots of wiggling around of the waveform. Again, we compare pitch sound, E, to noise, shh, very different. But how can we characterize this automatically using some kind of digital signal processing? Well, there is a technique called zero crossings that inspects the waveform to look at every time it crosses from negative to positive. I'm going to turn that on now, and we'll see that it's putting a dot every time this waveform goes from being negative to positive. Ooh. This is actually marking our periods for us. It's easy to do automatically in the computer. We just say, was the last sample less than 0, and is the next sample greater than or equal to 0? If so, then that's a positive going zero crossing. The problem is that even some periodic waves, you'll see that it's crossing twice for every period, even though I'm singing the same pitch. The nice thing about zero crossings, though, is that there are many of them for noise. So we can inspect a noise waveform, and there'll be thousands per second if it's noise. There'll only be hundreds or so per second if it's a pitch sound. So we now have another feature that we can use, just like power. We said, was power greater than something, then there's signal there and we'd print something out. Now we could look and say, are the number of zero crossings greater than something? And if so, it's probably noise. So now we have a silence, loudness, pitched or unpitched, pitched or noise, detector, the foundation of that. We can go further, and there are other algorithms that are better even yet that help us get around this multiple zero crossing per period, even for periodic signals. One of those algorithms is called the average magnitude difference function. And what that does is compares a signal with itself at different delays. So at delay of 0, the signal is identical to itself. At delay of 1 period, the signal is very similar to itself, and so the difference between those signals will be low. So as we see in the AMDF signal, which is shown right here below the waveform, for a periodic pitch sound, doo, we get periodic dips every time the waveform is similar to itself at those particular lags of 1 period, 2 period, 3 periods. So even though the zero crossings are showing many per period for that sound, the AMDF shows a very clear minimum at that point, and that's a good estimate of our pitch. A similar algorithm is called autocorrelation, and instead of looking at the difference between the waveform and itself, it actually looks at the relative power between different delayed versions of the signal. So the signal delayed by 0 squared with itself to form power is the maximum of the autocorrelation signal. The signal delayed by a little bit is less similar to itself, so the power is less. The signal delayed by exactly 1 period is again quite similar to itself. So we'll see a peak in the autocorrelation function. Let's look at that. So the autocorrelation function is maximum where the AMDF is minimum, and everywhere the AMDF shows a minimum that corresponds to 1 period or 2 period or 3 periods, the autocorrelation shows a peak. So those are two related pitch detection algorithms that are used in modern speech processing and lots of other digital signal processing systems. The average magnitude difference function takes advantage of a physical phenomenon called destructive interference, where two sounds, or a sound and a delayed version of itself, can cancel each other out for certain values of delay. For example, a simple, smooth sine wave, which we'll talk about very soon, at 100 Hertz would cancel itself out if mixed with a 5 millisecond or 0.005 second delayed version of itself. 0.005 seconds is half of the repetition period of 100 Hz, so the wave, delayed by half a period and added to itself, would cancel itself out entirely. This happens in physical rooms as well, where sound bouncing off of walls can mix with itself and cause cancellations at certain locations and frequencies. We've learned quite a lot about digital signals and signal processing, including how sounds are sampled and quantized for storage in the computer as sound files. We've also learned about pitch, noise, and loudness, and we use DSP to compute and display some of these attributes of sound. We work mostly in the time domain, looking at characteristics of waveforms, but we also took a brief glimpse into the frequency domain, looking at spectra and a spectrogram. Those horizontal stripes we saw in the spectrogram during the pitched parts of our recording of me saying synthesize actually correspond to sine waves, which come about in a number of ways, but are absolutely fundamental to sound. This animation depicts one way that sine waves come into being, where the height of the dot on the rim of the circle sweeps out a sine wave as the circle rotates. Our AC, or alternating current power, that comes to our houses via power lines comes as sine waves oscillating at 60 cycles per second, precisely because of the round generators spinning in power plants miles away. In the next session, we will be learning about and using sine waves a whole lot. And this first part of your assignment for session 1 is about sine waves as well.